Now we're in a position of appreciating how the eigenvalues and vectors enters the scene of systems of linear ordinary differential equations. So remember that our system of ODEs, the system of linear ODEs, could be captured in terms of a matrix into a column that contains the derivatives of some functions times the matrix A times another column of the original functions. Over here we have the derivatives, over here we have the functions themselves. And because we have many equations, they could be represented as a matrix equation, one matrix equation. So this thing here is a good container of multiple equations. Now, this equation here, which we have designated as equation 1, has an analog in the one-dimensional situation. For instance, in the real numbers, its analog is this, where a derivative of a function is equal to the function itself. As we have discussed before, that a solution to such an equation is the number 0, because the derivative of 0 is 0, so the left-hand side here would be 0, but the function itself is also 0, so 0 satisfies this equation. But 0, as we also spoke about this earlier, 0 does not give us any useful information. A rather somewhat helpful solution, or a non-trivial solution rather, is this one. When we take the derivative of the exponential of t, e to the power t, we get back e to the power t. And that means the derivative of this function is going to be equal to the function itself. So the point is, we have a bit of an experience of functions that are proportional to themselves, that rather is functions whose derivatives are proportional to themselves. So when we come to this multi-dimensional situation where we have multiple equations, a good guess could be something that looks like this. Why must it look like this? It must look like this because this function is a function that is proportional to itself. As basically we're drawing inspiration from this. So it must have this kind of a e to the t included in order to behave this way. But also, because now this is an array of objects, it needs to have a vectorial part. It needs to have this array part. And that array part is contained in this vector v bar. So this part will take care of this kind of periodicity. And this part, v bar, will take care of the fact that we're dealing with more than one equation, but an array of equations. So let's take this as a guess. And many a time, this is how we go about solving things in mathematics. It's you have a bit of experience and you just guess, how about this solution? Will it work? So we take this equation, we substitute it back here, and we consider what comes out. So substituting it, clearly, or I should have mentioned before, that in our guess, it is important that only this part depends on t, not the v bar. The v bar does not depend on t. If it did depend on t, we would need to employ the chain rule here, in which case we would lose this cyclicity, where the derivative of a function is equal to itself. Over here we would not get back the original function. We would get a sum of terms. That is, it will be the derivative of this times the derivative the derivative of this times this, plus the derivative of this times that. So we would need to employ the chain rule and the product rule of differentiation. So that's very, very important, that the t dependency is only contained in the exponential function. V bar is a constant, but it's an array in order to be dimensionally sensible with this equation. Okay, so that was very important because when we substitute it into this equation, we need to take a derivative of it. So this V bar is immune to the derivative, so only this term or this phase gets affected by the derivative, and in particular, the lambda constant is going to come down, and what we will have left is e to the lambda t times V bar. And on the right-hand side, we have our A matrix again times x bar, but x bar is just given by e to the lambda t times V bar, so we end up with something like this. But then notice that e to the t bar is now constant on both sides. When we cancel it out, look at what remains. Do you recognize this equation? This is the equation of eigenvectors and values. V bar is a vector which, when is multiplied by a, gives us something that is proportional to itself, lambda times V bar. What does this mean? Here's the interpretation. This guess will be a solution to this equation provided that V bar satisfies this condition. I'll repeat it. This guess, which is made up of e to the lambda t times V bar, will be a solution to this original equation, provided that V bar and lambda satisfy this equation. That is, V bar has to be an eigenvector of A, and lambda has to be the eigenvalue of A. So that is very, very important. This is how the idea of eigenvalues and vectors enters the scene of ODEs. Now, one more thing. If x bar 1 of t is a solution, and also x bar of x2 of t is also a solution to this equation, suppose these two individually solve this equation. So think of this as something which, when we substitute here and here, it preserves the equality, and this function here also, when we substitute it in here and there, this equality is preserved. It is also true that the sum of these two, that is, imagine we have another function, and I'm going to call it x sum, call this function c1 x1 of t plus c2 x2 of t. This function, this sum, will also be a solution to this equation. This is the principle of superposition. The reason why I mentioned this is that superposition principle, I should finish this part, superposition principle. The reason why I mentioned this is that sometimes this vector, this matrix here, has more than one eigenvector and more than one eigenvalue and more than one eigenvector. So because we have multiple eigenvectors, we'll be able to construct multiple of these kinds of solutions. So for each eigenvalues, we will find an eigenvector, and that alone will be a solution. But the sum of all the eigenvectors of all the solutions made up of all the different eigenvectors and values will also be a solution. So therefore, in general, the most general solution of a system of linear equations like this, of linear ODE, is going to take a form like this. And we usually write C1 e to the lambda 1 times t times v bar 1 plus c2 e to the lambda 2 times t times v bar 2 plus all the way until we to all the basically to the rest of the eigenvalues and vectors. So lambda 1 is an eigenvalue and its corresponding eigenvector is v1, and the same goes here. Lambda 2 is the second eigenvalue and its corresponding eigenvector is given by this. So this is why we always, this is the reason why we search for eigenvalues and vectors. It's because this kind of solution will solve this, or rather this kind of a vector will solve this equation if and only if this equation is satisfied. And as we spent a lot of time that this equation is an equation of eigenvalues and vectors. I hope that gives you now a reason why we search for eigenvalues and vectors in the context of the systems of linear ODEs. And then next we will consider an example and begin to apply these ideas.